To continue, we have a tail statistic of d bar equals to 1.4, which is a consequence of taking the difference of the pair samples and then take the average of the differences. Okay, the question is whether this tail statistic 1.4 is large enough to reject the null hypothesis. So we take a look. Now, the p-value, what is the p-value? The p-value is the probability of that the tail statistic is greater than that observed. Okay, what is the probability of obtaining such a tail statistic or an even worse statistic? Okay, now it doesn't matter whether we have an equal sign here in the calculation of the p-value, because with or without the equal sign, the probability would be the same. So the condition is that what is the probability of obtaining this tail statistic 1.4 or an even worse relative to the with respect to the null hypothesis, means that this is further away from 0 represents even worse. So that means the probability that d bar is greater than 1.4 under the null hypothesis. So what is the null hypothesis? The null hypothesis is that the mean is 0 under the null hypothesis. So if you go back to the assumption, we have the assumption that di follows a normal distribution with mean mu, unknown mean mu, but variance is known. Variance is 1.5 squared. Then we know the distribution of the sample mean under the null hypothesis, okay, which is 1 by a z transformation d bar minus mu. Mu is 0 under the null hypothesis, divided by the square root of the variance sigma square over n. On the left hand side we do that symbolically, but on the right hand side we do that numerically. So 1.4 minus 0 divided by the square root of sigma square over n. N is the number of pairs of observations, which is 12. Okay, so then we have probability of z greater than 3.2333, and using Excel we can calculate this probability to be 0.0006. Okay, which is extremely small, and if we set alpha equals to 0.05, then the null hypothesis will be rejected at the 0.05 level of significance, and we may conclude that the new herbal medicine is effective in increasing the number of hours of sleep of the patients. But again, we're not able to find this p-value during the examination as we have no access to Excel. Okay. Now, what is the interpretation of this p-value? The interpretation of this p-value, say p-value equals to 0.0006, is interpreted as assuming that the null hypothesis is true. Okay, if the null hypothesis is true, then the probability that one can obtain the observed sample mean of 1.4, or a sample mean which is more supportive of the alternative, that means greater than 1.4, and this probability is only 0.0006. Okay, this probability is extremely small, that the occurrence of such an outcome is highly unlikely with the assumption that the null hypothesis is true. Okay, but this is what we actually achieved from a single sample we draw from the population. Do you think the occurrence of this event is due to chance with a probability of 0.0006? Or there's something wrong with the assumption that the null hypothesis is true? This assumption may be inappropriate, and therefore if we think this probability is too small, we conclude that the null hypothesis is not true. By comparing this with the level of significance alpha, we say that the observations do not agree with the null hypothesis. Now, an alternative approach is to reject the null hypothesis if the absolute value of the standardized tail statistic exceeds the critical value Z alpha from the standard normal distribution. For example, recall example 20, where we have the p-value reproduced here. The standardized statistic is just this term, which is 3.233. This is the standardized statistic. the Taylor statistic. The p-value is also one form of the Taylor statistic, and 3.233 is another form of the Taylor statistic. And this is what we call based on the z-test. The Taylor statistic based on the z-test. This is associated with z, the standard normal distribution. For testing the null hypothesis that the population mean mu equals to mu naught. Mu naught is the hypothesized value, say 0 in our last example. And the alternative hypothesis would be mu greater than the pre-specified level mu naught, or less than mu naught, depending on the nature of the question. In statistics, we may have a two-sided test where we may test for mu naught equals to mu naught, but that will not be considered in this course. We only have a one-sided alternative in this course. The standardized Taylor statistic is simply, this is the Taylor statistic, which is simply the observed sample mean minus the hypothesized mean divided by the square root of the variance of the sample mean, okay, which is essentially root n times y bar minus mu naught over sigma. And that the Taylor statistic is known to follow a standard normal distribution if the null hypothesis is true. If the null hypothesis is true. That, in other words, if the null hypothesis is true, we expect that the Taylor statistic will fall in the pink region, will fall around here. If this is too extreme, that means that if the Taylor statistics fall somewhere near here, that means the p-value would be extremely small. Okay, or if the Taylor statistics fall on the negative extreme side, that is also an indication that the p-value is extremely small. So also, if we have a one-sided alternative, the alternative hypothesis is mu greater than mu naught, mu greater than mu naught. If the alternative hypothesis is true, we expect that the sample mean would be greater than the mu naught, the specified mean mu naught. Okay, so we would expect to have a large positive Taylor statistic if we are testing for this null hypothesis, that the alternative hypothesis that mu is greater than mu naught. We would expect to have a large positive Taylor statistic. But if we are testing for the alternative hypothesis that mu is less than mu naught, mu less than mu naught, then we expect the sample mean to be less than mu naught, and hence we expect to have a large negative Taylor statistic. But under the null hypothesis, we expect the Taylor statistic will fall around the pink area. Under the normal circumstances, the sample mean should cluster around the pink places. Okay? So the hypothesis testing is that the procedure is to set the appropriate null hypothesis H naught and the appropriate alternative hypothesis H1, okay? And then we calculate the p-value, where the p-value is the probability of achieving such a Taylor statistic or an even worse statistic under the null hypothesis, okay? And suppose the null hypothesis is that the parameter of interest equals to the pre-specified value, theta naught. For example, the theta can be the population mean, mu, okay, or the population proportion, p, okay, against the alternative that the population parameter theta is greater than the pre-specified value, theta naught, or less than theta naught, one-sided test. Okay, so this is the setting of the hypothesis testing, the null hypothesis with an equal sign and the alternative hypothesis with a greater than or less than sign. Okay, and the p-value for testing on the population mean, the sample statistic would be the sample mean. Okay, the sample mean. If testing for the one-sided alternative theta greater than theta naught, we look at the blue direction. Okay, the p-value would be y bar, probability of y bar greater than that observed. Okay, if the parameter of interest is on the population mean, and if the parameter of interest is on the population proportion, then the p-value becomes the probability that the sample proportion is greater than or less than the pre-specified value, the hypothesized value, p0. Okay, the decision is to reject the null hypothesis if the p-value is less than the pre-specified level of significance alpha, normally set at alpha equals to 0.05. And let's revisit example 19. From past experience, 60% of the patients with a certain disease recover within 3 days using the standard treatment. A new drug is developed to combat the disease, hopefully at a faster rate. 100 patients are randomly selected from the population, and it is observed that 70 recover within 3 days. The question is to carry out an appropriate test to determine whether the newly developed medication is more effective at the 0.05 level of significance. And let P be the proportion of patients recover within 3 days, and therefore the null hypothesis is P equals to 0.6, indicating that the new drug is equally effective as the standard drug. Against the alternative, P is greater than 0.6, indicating that the new drug is more effective than the standard drug. And the test statistic is simply the sample proportion p hat, because we are testing on the population proportion. And by the central limit theorem, we know the properties of the sample proportion. And throughout the hypothesis testing procedure, we assume that the null hypothesis is true, and therefore we have a p-value equals to 0.20207 that we illustrated this earlier. Okay, 0.20207, which is somewhere near the yellow region. Now, as the p-value equals to 0.027 is less than alpha equals to 0.05. So therefore, our conclusion is to reject the null hypothesis at the 0.05 level of significance, and we may conclude that the new drug is more effective than the standard treatment. Now, what can we do? Instead of computing the p-values, using Excel. Okay, so let's take a look at another example. You can find this example on YouTube. A principal at a certain school claims that the students in his school are above average intelligence. A random sample of 30 students' IQ scores have a mean score of 112. Is there sufficient evidence to support the principal's claim? The mean population IQ is 100 with a standard deviation of 15. This is the assumption. Okay, so we simply let X be the IQ score of the students in that school and assume that the IQ score follows a normal distribution with unknown mean mu and variance sigma square. Now notice that sigma square is given because the standard deviation equals to 15, so the variance is 15 square, and the mean population IQ is 100. Okay, so we assume that X, the IQ score of the students in that particular school, follow a normal distribution with mean mu and variance sigma square. And the null hypothesis is that the mean IQ score of the students in that school is the same as those in the general population. So that means the average equals to 100. The average would still be 100. Mean equals to 100. And the alternative hypothesis is that mu is greater than 100. The IQ score of the students in that school has above average intelligence. That means mu is greater than 100. And now we have a random sample of size 30. with a sample mean of x equals to 112, sigma equals to 15. So under the null hypothesis, we know that the sample mean follows a normal distribution with mean 100 under the null hypothesis, and variance given by sigma squared over n equals to 7.5. And the standardized test statistic is 4.3818. And the p-value is simply the probability that the standard normal random variable will take on a value greater than this standardized test statistic, 4.3818, which is 0.00005885 using Excel. This is particularly small. Okay, so we would reject the null hypothesis. But notice that the test statistic will determine the p-value, Okay, so what about if we set the p-value equals to 0.05? What value of the test statistic are we able to reject the null hypothesis? So we would like to do it the other way around, which would be more straightforward. So the alternative approach is given here. There is evidence suggesting that the alternative is more favorable if the test statistic is too extreme, that the standardized test statistic, the absolute value of the standardized test statistic is too large. In other words, that is too extreme, either to the negative side or to the positive side. But how large is large? And that only depends on the level of significance. Okay, for example, we only have the one-sided test in this course. Okay, for example, we are testing on the alternative that mu is greater than mu naught. So we will only reject the null hypothesis if the test statistic is large negative. Okay, so if we set alpha equals to 0.01, then the quantile associated with alpha equals to 0.01. That means if we want to leave 1% on the right-hand side of the standard normal distribution, then we can find that the quantile is 2.326, which is the magic number. Remember that this part will also be provided in the examination, because you have to make a choice between alpha equals to either 0.01, 0.025, or 0.05 in the examination. So the yellow area represents alpha. If alpha equals to 0.01, then the associated quantile that is 2.326. And if alpha equals to 0.025, that means 2.5% on the right hand side, then the associated quantile would be 1.96. And if alpha is set at 0.05, leaving 5% on the right hand side, the associated quantile would be 1.645. Okay, but on the other hand, that means if we have a standardized test statistic equals to 1.645, then the p-value would be probability that a standard normal random variable would take on a value greater than 1.645, that is 0.05. From this graph, it is obvious that if the test statistic is less than 1.645, okay, for example, 1.65, if the test statistic is greater than 1.645, for example, 1.65, or anywhere that falls in the yellow region, and then if we set alpha equals to 0.05, any area in any place in the yellow region is associated with the rejection region. That means the null hypothesis can be rejected if the pivotal test statistic Z falls in the yellow area with a pre-specified level of significance alpha. The critical values of some alphas are listed in the table above. For example, if we set alpha equals to 0.05, the rejection region would be the standardized test statistic greater than 1.645, then the null hypothesis will be rejected. Or if the level of significance is set at alpha equals to 0.025, then if the standardized test statistic is greater than 1.96, then the null hypothesis will be rejected. Or alpha equals to 0.01, then we have a smaller rejection region that the test statistic needs to be greater than or equal to 2.326. So we think that this alternative approach is more appropriate because once we specify the level of significance, and then we can compare the standardized test statistic with the critical values listed here, okay, depending on the level of significance. So let's take a look at an example. Consider example 19 under the null hypothesis. We have the test statistic, the standardized test statistic being 2.04, while the critical value at alpha equals to 0.05, the critical value is 1.645. Alpha equals to 0.05, the critical value is 1.645. Okay, 2.04 is somewhere here, around here, that falls in the rejection region, which is the yellow region. Okay, so therefore, as 2.04 is greater than the critical value 1.645, which is considered to be quite extreme. So therefore, the null hypothesis is rejected at alpha equals to 0.05. Okay. On the other hand, if we have a testing for mu less than mu naught, so we would expect to have a negative test statistic, But as we mentioned, that the normal distribution is a symmetric distribution. So the large negative, if we flip this over, that is associated with the large positive. So as long as it is more extreme, so we consider the absolute value irrespective of the direction of the alternative hypothesis. The test statistic would be too extreme. Too extreme means large negative or large positive. Large negative, if we take the absolute value, that is also large. Large positive, if we take the absolute value, that is also large. So we consider the large absolute value of the standardized statistic. Okay, so in this case, the absolute value of the test statistic is 2.04, which is greater than 1.645. which is determined by setting alpha equals to 0.05. So as the test statistic is greater than the critical value, the null hypothesis is rejected. And the two approaches, namely the p-value approach and the critical value approach, must end up with the same conclusion. They must end up with the same conclusion. Now consider example 20. We have the sample mean that follows approximately a normal distribution with mean 0 under the null hypothesis, and sigma square, variance sigma square over n. Okay, and the standardized test statistic was given to be 3.233. And at alpha equals to 0.05, the critical value is 1.645. And the absolute value of the standardized test statistic 3.233 is greater than 1.645 and is also considered to be quite extreme. So the null hypothesis is rejected at alpha equals to 0.05. Let's consider another example. Example 21. From past experience, 40% of the students in SCNC 1111 finds the course interesting. From past experience. And the Dean of Science suspects that Eddie, who is teaching the course for the first time, is not doing so well, so that the proportion P of students who find the course interesting has dropped this year. Okay? So the Dean randomly selects 200 students from the class, and only 40 of them think that the course is interesting. 40 of them, I'm sorry about that. 40 of them think the course is interesting. Carry out an appropriate test for the Dean's claim at the 0.05 level of significance. What is the Dean's claims? The Dean suspects that Eddie is not doing so well, so that P will drop. The proportion of students who find the course interesting will drop from compared to the general public. So the null hypothesis is that while Eddie is actually not doing so bad, his performance is on average. Okay, so P would still be maintained at 0.4. P equals to P naught equals to 0.4. While the alternative hypothesis is that Eddie is a poor teacher with P less than 0.4. P less than 0.4. And the sample statistic is X equals to 40 out of a random sample of size 200. So only 40 students find the course interesting, and the sample proportion is 0.2. So therefore, we can calculate the test statistic, the standardized test statistic, which is P hat minus P naught. P naught is the hypothesized value under the null hypothesis. Okay, even that in the variance term, we make use of P naught. So we have P hat 0.2 minus P naught divided by square root of P naught, which is 0.4, times 1 minus P naught, which is 0.6 divided by N. And this test statistic is minus 5.7735. Okay, minus 5.7735. And the question is to carry out an appropriate test for the Dean's claim at the 0.05 level of significance. Alpha is specified in the question to be 0.05. So at alpha equals to 0.05, the rejection region would be the absolute value of the test statistic greater than 1.645 at alpha equals to 0.05, which is the same as the previous example. And of course, if alpha is 0.025, then the critical value becomes 1.96. And if alpha is 0.01, then the critical value becomes 2.326. So the rejection region will depend on the value of the alpha that we specified in the question. So therefore, as the test statistic is much greater than the critical value, the null hypothesis is rejected at the 0.05 level of significance. And in fact, if you want to calculate the p-value using Excel, you can still do that, and that is extremely small. Okay, so that's all about the hypothesis testing part. And the next part, we will talk about some analysis of enumerative data based on the so-called the Pearson chi-square test, which is particularly important in some analysis of real-life problem. Okay, thank you very much.